Hello, my name is Sakib Karim and I'll be presenting Milestone 6. I will be implementing a flyback converter, which is a buck boost derived topology. For the power stage design, I've selected a switching frequency of 500 kHz, a turns ratio of 1 for simplicity. Conduction mode is in CCM, a current ripple of 10%, a critical load resistance of 10 ohms, however 8 ohms was implemented, a duty cycle of 29%, magnetizing current of around 7 amps, magnetizing inductance of 4.98 microhenry, an output capacitance of 31.8 microfarad, a MOSFET blocking voltage of 34 volts, and an average MOSFET current of 3.13 amps. For the controller design, it consists of a voltage mode control, as well as a type 3 compensation network. The control to output transfers functions are shown below for both the max load case and the minimum load case. This is the CISO tool output for the minimum load case. For compensation, as you can see here, the phase margin requirement is met at 52.7 degrees, and the gain margin requirement is also met at 60.3 dB, and this has a crossover frequency of around 8.55 kilohertz. This is the compensator transfer function Bode plot for both the MATLAB transfer function as well as based on the selected resistors and capacitors for the final compensator transfer function, which are very similar. And for the compensated loop gain for the max load case, we achieve a gain margin of 10 dB with a phase margin of 49.5 degrees. For the min load case, we achieve a gain margin of around 23.1 dB and a phase margin of 59.5 degrees. This is the LT Spice switching simulation with the noted input stage on the top left-hand corner, the output stage on the top right-hand corner, and the compensation network on the bottom left-hand corner. This is the voltage output plot of the LT Spice switching simulation with an approximate soft start of 30 milliseconds before reaching the transient. You can see the output voltage is at steady state around 5 volts. Once the transient is met around 40 milliseconds, the output voltage does reach back to 5 volts at steady state. For the schematic, we have the power stage shown on the top and the control circuitry shown on the bottom. The power stage shows the input capacitors on the top left-hand corner here, as well as our connectors. Our transformer is denoted here, as well as the clamping circuits for both the Zener 22 volt diode as well as the ES1D. Our MOSFET is shown here. The diode rectifier RBQ15BM is shown here. Our soft clamp at 5.1 volts is shown here. And our output capacitors are shown here as well, and the preload resistance network used to achieve around 8 ohms. At 10 ohms, the converter was going into DCM, so 8 ohms was selected so that the converter would remain in CCM. At the bottom here, we have our output connector. For the control circuit, the compensation network is shown here for the type 3 compensator. We have our oscillation component shown on the left here. Our ramp signal iSense is shown here, and our soft start circuitry is shown on the bottom here. And our gate drive buffer circuitry is shown at the right here and as well as our reference and VCC signals. For the board layout, the input stage is towards the left here, as you can see the input capacitors. We have the output stage on the right and the control circuitry at the bottom, and our transformer shown here with the diodes on the other side of the layout. The entire second plane is a ground plane with one noted cut here. This is isolating the input stage as well as showing the MOSFET and the gate drive buffer shown here. For the control circuitry, we can see our controller here. Our oscillation network is set up towards the top. Our I-sense signal is shown here towards the right. Our feedback network is shown towards the right here. Our soft start circuitry is towards the bottom, and then VCC and the reference signal are towards the left. A lot of the components used around the feedback network tended to be smaller size components, around the 0605 or the 0805 to provide little spacing to achieve a better response for the feedback circuit. For the output stage is shown here with the diode rectifier, the output capacitors, as well as the preload resistance network, and our soft clamp circuit. For the transformer design and assembly, I did select the kg method with a kg minimum of 9.44 e to the minus 4. Course selection was a PQ 2016. Air gap of 5.790 millimeter, or e to the minus 5 millimeters. And the number of turns for both the primary and the secondary was 2. The primary side measured at 4.7 microhenry, and the secondary side measured at 4.6 microhenry. This is the implementation of the primary side transformer. I did use a larger number of turns for this, for both the primary side and the secondary side, as the inductance requirement was not being met. At that 2 turns, I had to use a little more as their secondary side transformer. This is the overall board. At the top level, we can see our assembled control circuitry here, our assembled output stage shown here, and the assembled input stage shown here. Note that a snubber was not used for the MOSFET. And our bottom side of the PCB, which is majority of a ground plane. However, we still have a trace here as well as our diodes for the transformer. So the expected frequency for the gate drive signal at a no load was 500 kilohertz. However, I was measuring around 470 kilohertz with a large amount of ringing at the turn on portion of the MOSFET. The output voltage at steady state with no load does meet the peak-to-peak requirement at 87.6 millivolts. And at the max load condition, the requirement is not met, as the output voltage is reading around 109.53 millivolts, with the gate drive signal shown there also showing a large amount of ringing. The turn-on waveform does exhibit a larger than expected voltage. It's reaching 6.1 volts instead of not more than 5.1. In terms of the design verification, these are the input and output measurements shown here. However, the overall efficiency requirement was not met, as the highest efficiency the converter can achieve is around 63%. This is the load step response, and that requirement was not met, as well as the minimum voltage is negative 2.13 with the max output voltage at 0.86 volts. And in terms of lessons learned, the design for the controller, we could have had increased crossover frequency as well as a larger phase margin to reduce the transient. I could probably add more spacing between the controller components to reduce ringing for the gate drive signal, as well as adjusting the preload resistance to increase the overall efficiency of the converter. In CCM, the overall efficiency does tend to suffer compared to a CCM at high loads and DCM at low loads, so I might approach that method for a iteration. And that's it for my presentation. Thank you for watching.